an insecure network. Now let's discuss about the vulnerabilities of the Diffie-Hellman key exchange to man-in-the-middle attacks. These attacks can compromise the confidentiality and integrity of exchanged keys. In a typical Diffie-Hellman key exchange, Alice and Bob exchange their public keys securely, allowing them to derive a shared secret key without any interference. Consider Alice chooses her private key to be A. She then computes her public key as G to the power a mod P. She then sends this public key to Bob. Bob chooses his private key to be B. He then computes his public key as G to the power B mod P. Now Bob sends his public key to Alice. Both Alice and Bob perform computations to arrive at their secret shared key G to the power AB mod P. This is what happens in a normal DH key exchange. Now consider an attacker named Tom intercepts this exchange through man-in-the-middle attack between Alice and Bob. Tom uses M as his private key. When Alice sends her public key to Bob, Tom intercepts the exchange, but Alice thinks the key is sent to Bob. To establish the key exchange, Tom sends his public key to Alice. Tom and Alice compute the shared secret key, and the communication channel is established between them. Alice still thinks this secret key is established with Bob. Now Tom sends his public key to Bob, and Bob sends his public key to Tom. A secret key is now established between Tom and Bob but thinks it is with Alice, with Tom in the middle intercepting the messages. All the information now exchanged between Alice and Bob goes through him. Each party believes they are deriving a shared secret key with the intended recipient, here, Alice and Bob, but in reality, they are both deriving a shared secret key with the attacker, Tom. Thus the communication channel is said to be compromised. Now, let's discuss some of the countermeasures that can be used to avoid man-in-the-middle attacks. Since the problem lies in the authentication of the sender and receiver, digital signatures can be used. Both Alice and Bob can use them to authenticate the exchanged public keys. During the Diffie-Hellman key exchange, signing public keys with the private key helps ensure the integrity and authenticity of the keys. Implementing a public key infrastructure, PKI, can indeed help prevent man-in-the-middle attacks for Diffie-Hellman, DH, key exchanges. The PKI involves a Trusted Certificate Authority, CA, that issues digital certificates to entities, such as servers and clients. When Alice and Bob perform a DH key exchange, they can verify each other's certificates to ensure they are communicating with the intended party. In this video, we will be explaining hash function, their applications, and security requirements. A hash function accepts a variable length block of data as input and produces a fixed size hash value. It is used in a wide variety of security applications and internet protocols. The most common use of hash function is in message authentication and digital signatures. The first figure depicts the general operation of a cryptographic hash function. As it can be seen in the second image, the sender generates the hash and appends it with the message, and upon receiving the message, the receiver also generates the hash from the message. The hash values generated by the sender and the receiver are compared to verify the integrity of the message. We will now look into some block diagrams to understand how hashing can be used for message authentication. In the first diagram, the message plus concatenated hash code is encrypted using symmetric encryption. As only A and B share the secret key, the message must have come from A and has not been altered. In the second diagram, only the hash code is encrypted using symmetric encryption. This reduces the processing burden for those applications that do not require confidentiality. Here in the first diagram, A and B share a secret value S. Sender A computes the hash over the concatenation of the message M and S, appending the resulting hash to M. B, possessing S, can verify by recomputing the hash. Confidentiality can be added to the above approach by encrypting the entire message plus the hash code as shown in the diagram below. We will now look into requirements and security of hash functions. We will first see the meaning of collision. Hash function H is a many-to-one mapping. For any given hash value, there will in general be multiple premages. A collision occurs if we have x is not equal to y but hash of x is equal to hash of y. If for any given hash value h, it is computationally infeasible to find y such that hash of y is equal to h, then h is preimage resistant. For any given block x, it is computationally infeasible to find y not equal to x, with hash of y is equal to hash of x, then the hash function is second preimage resistant. To be collision resistant, it should be computationally infeasible to find any pair x, y, such that hash of x is equal to hash of y. The diagram represents the relationship among the hash properties. In the realm of cryptography, the secure hash algorithm, SHA, stands as a fundamental tool to ensure the integrity and security of digital data. Renowned for its resilience against cryptographic attacks, SHA is extensively utilized in critical applications such as password storage, digital signatures, and blockchain technology. Functionally, SHA processes inputs of varying sizes and transforms them into fixed-size hash values. One notable variant is SHA-512, indicating a 512-bit hash output. The algorithm orchestrates a sophisticated interplay of logical operations, bitwise rotations, and modular additions to systematically convert input data into a unique and ostensibly random hexadecimal hash value. Creating a secure hash function is akin to designing a secret code, where message chunks are scrambled using a magical lock, ensuring each chunk is influenced by the preceding one, creating a challenging puzzle for anyone attempting to unravel the code. The fundamental operations include OR, XOR, and NOT operations. The right shift involves shifting a specified number of bits to the right. The XOR bitwise operator outputs a 1 only if one of the input bits is 1, useful for balancing representations of multiple bits through XOR operations. The addition function adds significant bit chunks, followed by modular reduction to 232, creating a 64-bit number. These operations can be combined to form functions. The first 4 functions are named using Greek symbols sigma, lowercase and uppercase, collectively known as rotational functions. These functions involve right rotations, symbolized by rotator, with varying powers. The last 2 functions, choice, ch, and constant, introduce conditional selection and predefined constants, kt, respectively. The constants are generated by taking the cube root of the first 64 prime numbers fractional part, providing a selection of random bits for enhanced security. After defining constants and functions, the next step involves preparing the message for hashing. The message, typically in string form, is converted into a binary format using the hash key value table. Padding is applied by adding zeros to the end, creating a 512-bit chunk. To prevent similar inputs, a 1 bit is added, and the message size is included in the last 64 bits of padding. The padded message is then cut into equal 512-bit blocks for processing. Each block undergoes expansion to 64 words by applying rotational functions to some existing words. The hash function, starting with an initial hash value derived from the square root of the first 8 prime numbers fractional parts, employs a compression function. For each word in the message schedule, the compression function calculates temporary words, T1 and T2, using rotational functions and majority operations. This process, known as a compression round, is repeated for every word in the message schedule. The round function in the SHA-512 algorithm is a crucial component responsible for transforming the input data through a series of operations into the final hash output. Let's break down its key elements and operations. The first step is initialization. Each round begins with the initialization of variables representing the state of the algorithm. These variables, A, B, C, D, E, F, G, H, hold intermediate results and are updated throughout the round. The second step is message schedule. The round function utilizes a message schedule to generate 64-bit words, WT, from the current 1024-bit input block. The schedule involves a combination of rotation and shifting operations applied to previously generated words. This introduces redundancy and interdependence into the message blocks, enhancing security by making it challenging to find different blocks that produce the same output. The third step is additive constants. Each round employs an additive constant, KT, specific to that round. These constants are derived from the fractional parts of the cube roots of the first 80 prime numbers. They introduce randomness into the process, preventing regularities in the input data from affecting the output. The fourth step involves the logical functions. The round function uses two logical functions, CH, E, F, G. This function, called the choice function, operates on the bits of the variables E, F, and G. It selects bits from F and G based on the value of E, ensuring nonlinearity in the algorithm. Maj, A, B, C. The majority function operates on the majority of bits from the variables A, B, and C. It ensures that each output bit depends on the majority of the input bits, increasing the complexity of the algorithm. The fifth step involves the bit operations. The round function includes bitwise operations such as AND, OR, XOR, and bit shifting, rotation. These operations manipulate the bits of the variables according to specific rules defined by the SHA-512 specification. The sixth step involves the word updates. After applying the logical functions and bit operations, the registers A, B, C, D, E, F, G, H are updated based on the calculated values. This updating process ensures that each round contributes to the transformation of the input data into the final hash output. Next is the finalization. After completing all 80 rounds, the output of the last round is added to the intermediate hash value to produce the final hash output. This addition is performed separately for each word in the buffer, ensuring that each part of the hash output depends on all parts of the input data. In summary, the round function in SHA-512 is a complex sequence of operations designed to thoroughly mix and transform the input data, making it computationally infeasible to find two messages with the same hash output or to reverse engineer the original message from the hash output. In the realm of cryptography, one encounters a remarkable fusion of hashing and encryption techniques embodied in the hash function based on Cipher blockchaining, CBC. This innovative approach intertwines the principles of both hashing, which ensures data integrity and uniqueness, and encryption, which secures data confidentiality. The CBC mode of hashing transcends mere data processing by implementing a principle that intricately links each block of data to its predecessor. This method operates on the concept of chaining, where before hashing a block of data, it is fused with the hash of the preceding block. As a result, a chain of interdependent blocks is formed, where the hash of each block is contingent upon the hash of the previous one. This chaining mechanism not only adds complexity to the hashing process but also enhances the security and integrity of the data being processed. By forging this interlinked chain, the CBC mode of hashing fortifies cryptographic operations against various attacks, reinforcing the confidentiality and integrity of sensitive information. This method starts with an initialization vector 6. What stands out in CBC is that identical data inputs at different times yield different hash values, owing to the chaining mechanism and the influence of the foe. This feature significantly boosts the security and integrity of the hash function, making it resistant to a variety of cryptographic attacks. Vulnerabilities and challenges. While CBC without a secret key enhances security, it is not without challenges. It is vulnerable to birthday attacks, especially with a 64-bit hash code using this. These attacks exploit the birthday paradox to create forged messages with the same hash code.
Message Authentication Code or MAC is a short piece of information used to authenticate the origin and nature of the message. It is also known as tag. Authentication, in cryptography, is simply a way to verify the identity of who created the information, such as the user or system.
Let's try to understand MAC using an example. Here, Alice is the sender of the message and Bob is the receiver. Since Alice is the sender, she uses a publicly known MAC algorithm to generate a message authentication code.
The message authentication code takes the message and a secret key as the inputs. This secret key is usually already shared between the sender and receiver. The MAC algorithm takes the input message and compresses it to a fixed length output with the help of the secret key. The generated message authentication code is appended with the message, and the combined message and MAC is now sent to Bob, who is the receiver.
The receiver then uses the same message and the pre-shared secret key to generate the MAC of the message in the same way. If the MAC generated by the receiver matches with the MAC sent by the sender, the authentication is successful. In this way, message authentication code, or MAC, ensures proper authentication.
Imagine Bob, the sender, wants to securely transmit a message to Alice, the receiver, using a message authentication code to ensure the integrity and authenticity of the message. However, Darth, an adversary, intercepts their communication and attempts to launch attacks on the MAC. Bob generates a MAC by applying a cryptographic function to the message and a secret key, creating a tag that is sent along with the message to Alice. In the case of a brute force attack, Darth aims to discover the secret key by trying various combinations until finding one that produces a valid MAC tag for a given message. This attack is analogous to Darth attempting to guess the combination of a lock by trying different numbers. Data integrity refers to the validation that data has not been modified or corrupted during transmission. Suppose Bob and Alice are communicating over the public internet. Also, suppose both of them have a symmetric key and they have decided on the symmetric encryption algorithm to use. Here, Bob sends his encrypted message. Encryption ensures confidentiality, meaning that no one can understand the message because it is encrypted. However, that does not mean that a malicious person, say Darth, cannot interfere with the message and change it, even though they do not understand it. Let's have a bank transaction example to show how damaging this attack can be. Let's say Bob is sending $100 to Alice. Darth intercepts the message, and although he does not understand a thing, he flips some bits and transfers the message to the bank. When the bank decrypts the message, it may show as $1,000 instead of $100. That's why, in addition to encryption, we need to make sure the data has not been altered. Back to our previous example. How can Alice make sure that the message has not been modified? The standard approach will be hashing. Let's recall how hashing is used for data integrity. Bob will apply a hash function to the data he intends to send and will generate a fixed-sized hash value, often referred to as the digest or the checksum. Then he will send the hash over the internet. If both matches, it indicates that the data has not been altered by Darth. However, think for a second. Do you think this is enough? What do you think Darth would do to alter the data and still pass the integrity check? After all, hackers are smarter than that. Why not alter the message and also send an altered hash? How then can Alice know that the hash and the data have been modified? Here comes the role of HMAC, and for hash-based message authentication code. It is a cryptographic authentication technique that uses a hash function and a secret key. For HMAC to work, both Bob and Alice should agree on a shared secret and a hash function. After that, the generated MAC or message authentication code will be sent along the encrypted text. Let's say Darth intercepts and changes the message along with its MAC. Remember that Darth does not have the secret key and will hash the encrypted message without any additional information. Alice, after receiving the message, will apply the HMAC function with the message and the secret key. The message authentication codes will not match, and Alice will know that the
MACs based on block ciphers, DAA and CMAC. Ever sent an email but worried it might be tampered with? That's where message authentication codes, or MACs, come in. Today, we'll see how block ciphers, those encryption powerhouses, can build these digital shields. Data Authentication Algorithm. The algorithm can be defined as using the cipher block chaining CBC mode of operation of DES with an initialization vector of 0. The data example message, record, file, or program to be authenticated are grouped into contiguous 64-bit blocks, D1, D2, up to dn. If necessary, the final block is padded on the right with zeros to form a full 64-bit block. Using the DES encryption algorithm E and a secret key K, a data authentication code DAC is calculated. The DAC consists of either the entire block on or the leftmost m bits of the block, with 16 equals m less than or equal to 64. DAA is no longer recommended due to security limitations. Cipher-based MAC. CMAC mode of operation is used with AES and triple DES. First, let us define the operation of CMAC when the message is an integer multiple n of the cipher block length b. For AES, b equals 128, and for triple DES, b equals 64. The message is divided into n blocks, M1, M2, Mn. The algorithm makes use of a k-bit encryption key k and an n-bit constant, k1. For AES, the key size k is 128, 192, or 256 bits. For triple DES, the key size is 112 or 168 bits. CMAC is calculated if the message is not an integer multiple of the cipher block length. Then the final block is padded to the right with a 1 and as